Good afternoon, ladies and gentlemen. Welcome to the BSRIA webinar on thermal comfort. My name is Callum McLean. I've worked for BSRIA for about 10 years and I've been involved with thermal comfort measurements for most of that time. So both on site and in-house. And I'd like to just talk about some of the experiences and observations that I've had during that time. Okay, a brief summary of this presentation. It's going to involve first as an introduction into what BSRIA's involvement with thermal comfort has been. Next, I'm going to go through some of the misconceptions of thermal comfort and what people actually think about it. Next, I'm going to go through a brief outline of the standards involved and what measurements need to be taken, and subsequently the calculations that need to be done on those values. Then I'm going to go through a few bits of equipment that BSRIA has that actually have to do these measurements and some examples of the data we've actually taken on site and in-house. And finally, just a brief roundup of this presentation. As Tracy has said, if you could just put your questions in the question box and then I will try and answer them by email whenever I get back to my desk. Thank you very much. BSRIA has been involved with thermal comfort for more than 25 years, a lot more than 25 years. I've been involved, as I said, for about 10. This has included office mock-ups, where we've actually built a section of office, representative of an on-site office, and done thermal comfort measurements around a simulated set of people. It's also involved actually going on site and doing site measurements where the equipment is either installed or simulating the people. As you can see here, these are the people simulators that we use. We have also used it within supermarkets. So this is an actual mock-up of a supermarket. As you can see, we've used a lot of food. This is lard, but in this case, it's just an example of some food in the supermarket setting, and for the thermal comfort of the people who are either visiting or working in that environment. We've done thermal comfort in hospitals. This is an isolation room of the patient and the visitors, and in this case, the doctors and nurses that are working within this space to try and make that person better. We've involved in schools. As you can see, we're not allowed to take pictures with actual children in the space, but we have done work with the children in the actual space to do the thermal comfort for the teachers and for the students and see whether they're alert, because we've also done alongside CO2 measurements to see whether they are able to process all the information they're trying to bring in and try and actually educate them as well as possible. We've done libraries. So this is with the books have to be kept at certain conditions for the high value, high price books and the older books, where they are trying to be kept at a relative humidity that's reasonable, but also a cooler temperature. So how do you get that while still maintaining the thermal comfort that people that need to work in there or visit? We also get involved with component testing, where it's, say, chilled beams or fan coil units or other grills, etc., where they are used as a separate product to be then used within the manufacturers or consultants' design and build, pre-build, and sometimes even post-build when they're trying to do redevelopment work. Okay, moving on to some of the misconceptions of thermal comfort. A lot of people think that it's just the temperature within the space or just the clothing that someone is wearing, so put on another jumper if you feel cold. These are big factors, however, they are not the main factors as a whole. They have a significant input, as you'll see with some of the calculations and the standards that are needed later on in this presentation. But the actual nitty-gritty is the entire ensemble needs to be correct for you to get good thermal comfort measurements. There are even some who think that it's just thermography. Thermography is thermal comfort. You can use thermography for thermal comfort indications, but it isn't thermal comfort. Thermal comfort I'll go into is based on the standards and the actual measurements that are taken of certain values. So, moving on to what the standards are. These are the two main standards that we use. You don't need to read them, you can read them at your leisure. But they break down into 7726. The first standard is just the instrumentation used to take the physical measurements. And then 7730 is the calculations and the outputs that you would give to a client or we would use in-house to do development work to then tell you what the thermal comfort criteria actually are. So thermal comfort is just a general, what the general thermal sensation of a person within a certain space due to the physical air around them and the influences on that air. So either HVAC equipment or natural ventilation through drafts, and it's just an expression of how that person would actually feel in as they're sat at their desk or walking through the room or working within that space. Okay, so some of the measurements that we actually take to do the thermal comfort analysis, the main 5 are air temperature and air speed. So these are just a measure of the average over a certain length of time of a number of measurements of air temperature and air speed. And I'll go into some of the equipment in the following slides. And then also there's something called turbulence intensity, which is just the change in air speed over time. So it's essentially a standard deviation measurement on the air speed. So as the air changes direction or speed, the turbulence intensity takes that in consideration to work out a draft risk further down the line. Because if it doesn't change by very much, you would then have normally a directional jet, and if it changes too much, then you would end up with such turbulent air that the person may actually feel stuffy because there's not enough directional component to take away any heat off of that person's body. The next one is the black globe temperature or operative temperature, which is taking into consideration the radiative component from, say, a radiator radiating heat or a chilled ceiling absorbing energy from the space, or even the computer that could be sat in front of someone in an office, or the people around them if they're in some sort of conference type setting or anywhere that would have large numbers of people, say a cinema, etc. It takes into consideration because it is actually just a painted globe temperature, which is an air pocket that has a temperature probe in the middle, and you're trying to measure the radiative as well as the air temperature in that space. And lastly, there's a very small component from relative humidity. It doesn't have a major effect on most thermal comfort measurements. The standard even allows you to put 50% in for most of the measurements just because it has such a small effect. One of the sets of equipment that we have does take it into consideration because we are quite often doing occupied zones with that piece of equipment, and sometimes humidity it has an effect because there are so many people within that space. Okay, the 3 main numbers that we actually get out of these numbers that we actually measure, the calculated numbers, come out as these 3, and it's the draft risk, which is a percentage of people that would be affected by say air movement or the temperature within the space, and therefore would feel it as a draft, perceive it as a draft. Then you have the PMV, which is the predicted mean vote, which is normally a 7-point scale. Some people use a 9-point scale from -4 to +4, but we would normally use -3 to +3 to give an indication of how someone would vote if they were doing a survey within that space. 0 is you're perfectly comfortable, just right, as you can see on the scale at the bottom as an indicator. -3 is if it's too cold or too drafty, or the actual air moving is so much colder than the actual space that they're within. And +3 is usually an indication that it's too hot, or there's not enough air movement to actually take away the heat from the person or the equipment that they're using. So that would actually then cause it to be stuffy. That is then used to calculate the PPD, which is predicted percentage dissatisfied, which just gives a number of how many people would be dissatisfied with the space that they are occupying. So would it be too hot, too cold? That number doesn't really mind. It doesn't actually use that number. What it does is it just takes the values outside of -1 to +1 of the PMV. If you have a very good room, you will normally get a PPD of 5%. 5% is the lowest number that you can get on PPD. There will always be some people who feel that it is either too hot or too cold, just because everyone is different. They either have different thermal equilibrium with the space, so they have a different actual way that they sit within that space and how they feel comfortable. They may slouch differently in their chair, they may move differently, or they may actually be working at a different pace than the person sat next to them. The other indication of PPD is if someone is wearing a lot more clothing, or they've just come in from outside, say during the summer, and they feel the room could be very cold, or it could be very hot in the winter if they've just come in with a massive jacket on. Okay, so I would just like to move on to the equipment that BSRIA uses. The first one is called a TCA, which is a thermal comfort analyzer. It's an in-house piece of equipment that we've built essentially using proprietary bits of equipment. This is in a mock-up, in one of our mock-ups, just as a test, just to show you what this involves. This actually is essentially just a digital multimeter taking measurements of these probes over roughly a 2-minute period. Once a second is normal. And it takes all of the indices and then calculates the PMV and PPD as an output at the end of this 2 minutes. This is a zoomed in version of that, showing each of the probes. The first probe at the back is the anemometer, doing the air speed and the air temperature as a indication of, and also gives you an indication of the turbulence intensity. And it takes these measurements, as I said, over a 2-minute period and averages them and gives you out a number at the end. The next one is the black globe. This takes into consideration the radiative component from, say, the screens that we've simulated behind, or the lighting, or the solar loading, so the heat coming through the windows, or even the people who are sat at the desks actually having an effect on, say, the person next to them. The third piece of equipment is actually a combined temperature sensor and our relative humidity sensor. So this one actually includes relative humidity, because this one is quite often the bit of equipment we take on site and put it at a desk to do measurements in an occupied office. This was also the piece of equipment we took to the school to do the measurements around the school children to make sure that they were not overly hot, overly stuffy, and they were actually able to concentrate within their work environment. Okay. Next, this is the second set of equipment that we use, which is usually used in something called a Polepush. As you can see, they're mounted on a single pole normally, different arrangements, different numbers of probes, but the same basic use. And the reason it's called a Polepush is because we move this piece of equipment over an entire space or an entire room or around all of the desks to take thermal comfort measurements at multiple points, and they are able to plot contours around the room. And I'll show you some of those in my examples towards the end of the presentation. This piece of equipment is high accuracy, high number of probes. It's trying to be as minimal as possible to not disturb the air. That's why in the later generations, as you can see in the right-hand 2 images, it actually has a smaller pole and smaller pieces of equipment, the anemometers themselves, to try and disturb the air as little as possible, but the measurement equipment itself. You can also see in the middle of the pole, at about the 1.1, 1.2 meter height, is either the globe in the left-hand image or the operative temperature sensor in the right-hand 2 images. These are the same probes as you saw in the TCA analyzer previously, just mounted on this pole. And the reason it's mounted at 1.2 is to give head height when you're sat down, or chest and abdomen height when you're stood up. And that's been seen as a good indication of the thermal comfort throughout the entire height of that space via using this one, because your head height is the one that's usually the most exposed when you're sat at a desk. We do take measurements across the entire height because there are other indicators, like the bottom probe at 0.1 of a meter is normally ankle height when you're sat at a desk or stood up. And that gives a good indication of if there's a big difference between the head height and the ankle height of the actual air speed or air temperature, you will feel that as a much increased level of discomfort than you would do as if you just had the same number across the entire space. Okay. So the 2 main inputs other than the measurements are actually taken is your clothing level and your activity level. These are called CLO and MET in the standard because it's the clothing level and metabolic rate of the person actually in the space. The standard numbers that we actually have to input are technically an average across the entire occupied space. So say you had 40 people, everyone will be wearing something slightly different unless it's in a specific uniform office, You may have people who are ladies wearing, as you can see in this picture, no sleeve top and a skirt, or you can have the gentleman sat next to her with a tie and a long sleeve shirt on. So we actually have to put in numbers that are normally an average of that space. However, because the calculations are so relatively easy to do, we can actually do ranges depending on who is in the office. So if they decide that they want to do a check, if it's all ladies in the office or all men in the office, they can do slightly different clothing levels, because a man will normally try and wear a tie to try and look smart in the office. Or if it's a sort of an informal office, I'm wearing a short sleeve shirt at the moment, then you're able to have slightly different values, and you can input all of these and have different numbers come out. So the numbers normally come out at, if we have, say, a gentleman in a short sleeve shirt or a lady in a formal dress, you'd have a number of 0.7, and a suit jacket with a tie, or a full suit for a lady or a man, is normally taken as a 1. These numbers are just the input numbers, and you can calculate it. The standard actually has full numbers for working out full clothing depending on what that person is wearing. We don't normally go into that far. We just ask the client exactly what they expect their people to be wearing, and we give them a clothing level. The metabolic rate consequently also has a different number depending on how hard the person is working. So a seated person who is just relaxing has a value of roughly 1 metabolic rate unit. Someone who is working in an office lightly would be 1.2, 1.3, and someone who could be walking quite fast would be up to, say, a 3.4. There is issues with, if the person isn't seated, they're not actually sat there for long enough to get into an equilibrium with their surrounding space, but it gives you an indication of how the heat output from that person is affecting the space around them. Okay. Additionally to the clothing level and metabolic rate, the actual things that affect the thermal comfort on the people within the space are things like say, air conditioning is in the picture in the top left, or chilled beams or fan coil units, or the swirl grills that could be in the floor, or even just the natural ventilation coming through windows. These all have an effect on the thermal comfort indices, but it's not just the air speed, it's the air temperature. Say an aircon unit running on full chilled will have a much more of an effect than just the fan running in that air conditioning system. So it's a combination of temperature and the air speed will have a much greater effect than just one or the other. And it also has a big effect if the room temperature is either significantly higher or significantly lower than the air traveling through it. The actual direction can also have an effect. If you have air coming directly on the top of your head, it will have a different effect than if you have a generalized air passing over you from the side or coming up from underneath from your ankles. You actually may feel that as worse than just having it coming from the generalized air around you through, say, natural ventilation. The standard actually has some indices, the PPD, PMV and draft risk. It actually has some output numbers that can give you an indication of how well made or how well built your space is for thermal comfort. It gives it a category between A and C. These numbers are sometimes used by clients to give a sort of benchmark. The CIBSE guides actually give a category B as being relatively good. Category A is exceedingly difficult to measure, as trying to get values below 6% PPD or between -0.2 and +0.2 PMV is very, very difficult to measure. And there is actually other indicators between, say, ankle height temperature and head height sat down temperature, as you could see in my previous slide with the probes, gives you an indication of those values without actually taking the physical measurements of the PMV, because they can be misleading, because it only takes one person to have a different clothing level and you will actually be outside of the PMV. Okay, so next I would like to go into some of the examples of data that we have taken in-house and on-site. My first one is of an office mock-up using chilled beams. Quite a lot of the work that I have and examples to show you are of chilled beams. However, it is just a generalized look at some of the work that we've done, and it's the actual thermal comfort lessons that can be learnt can be applied to any type of piece of equipment, including fan coil units, etc. This test had low solar input. It had quite a high heat load within the space, and that can be easily seen by the speed graph up in the top left corner. The chilled beams were working extremely hard to cool the space down, and they were interacting with each other, causing this high speed. However, it did not have a big effect on the PMV and PPD, the graphs at the bottom, because the actual temperature of that air movement was the same as the actual air within the space. The indices that you see for the temperature in the PMV, it's on a graded scale between red and white, as you can see on the right hand side of each of those images. And for the PMV, it runs from +1 to -1 for the red to the white, respectively. So green is where you're looking for it to pass as a 0. That's actually the best that you can get for PMV. And the PPD consequently runs from a black at 5%, because you can't get better than 5% normally, up to about 30 to 35% for fully red. This one still came out relatively low PPD values because the air temperature was so uniform within the space. And it was also actually matching the air speed and temperature was matched very well. The same office was then tested with a high solar component. So the red wall that you can see on the left of each of these images is the solar wall. That's where the windows would be. They were full height from floor to ceiling, putting in a huge amount of energy from the air temperature outside and also from the sun beating in through the windows. You can see it's had a significant adverse effect on the temperature and consequently the PMV and the PPD. Some of these values even going up to 30% PPD, which is significantly above what a pass criteria for this specific office was. However, the client did state that the first 2 meters of the office wasn't actually occupied. It was a walkway for people to come through to meet their desks. So this office, what they needed to do was then add some solar shading to their windows, and they actually were able to then drop their PMV and PPD to a much better value and actually conform with their own internal standard for this test. A second mock-up. This one was actually a retrofit. They were actually trying to renovate the space and improve the amount of people and office equipment they had in the space to allow the people to have more density without having to have more office space. This one is as built, so the previous test, so we retested it to check that we could actually produce a space that actually conformed with the as-built environment. The PMV and the PPD values, as you can see, are extremely low for the PPD and extremely uniform for the PMV. This office had very low number of complaints from the office staff to the admin group, and that you can see that actually they were able to prove in our labs that that's those numbers they would get. They consequently then increased the heat load to all of the desks using more people, more computers, and actually fully populating the space, and they started to see higher temperatures in certain areas of the room, which adversely affected their PMV. Their PMV they were looking for was to try and keep it within the category A throughout about 90% of the room. This actually started to fail because it actually was outside of that value. It was still reasonably good on the right hand side of the PMV image. It's actually still got some green, but because the left hand side had started to fail, they actually classed it as a total failure. The same manufacturer was then asked, could they produce a new beam to install to try and improve this PMV and PPD value? As you can see, this didn't work out so well. They had issues with air mixing within the space and actually colliding and causing high speed movement. and localized cooling, but not generalized cooling. As you can see by the temperature pattern up in the top corner, it didn't mix with underneath the bulkhead uniformly. So the PPD was actually uniform over the space, but it was still too high. A second manufacturer was actually contacted then to try and see if they could produce a beam off the shelf. And the data that you can see here is what they were able to produce. Now, it may not look hugely improved from the previous image. The main issue was that the heat loads that we had to put in the space were so high output that they were actually having slight effects on the air temperature probe. And you can actually see it's just localized heating on the temperature plot up in the right-hand corner. These would not be seen normally in general use when they were being used in an actual building. And the client was able to say that because they had this criteria where they had to keep 90% of the room within the PMV and the PPD, it was actually deemed as a pass. And they've subsequently built this on site and found that it matched very well with the data that we have taken, and they still have very low complaints from their staff. Okay, moving on to a slightly different set of data. This one is taken from an office where they were having complaints from staff feeling too hot and too stuffy in certain areas and too cold and too drafty in others. But the main three numbers I want to bring out are the highlighted ones. And this is versus the number of tested points down in the bottom corner, which is 67. We had 54 numbers over about a 2.5 hour period that were outside of the criteria from the CIBSE guide. So these guys were working to a CIBSE guide regime where they wanted to keep the room temperature within 20 to 24 degrees, the PMV within minus 0.5 and plus 0.5, and the PPD below 10%. So the actual air temperature was outside of the average at 24.4. They were still failing that criteria. The PMV and the PPD on average was very good, but there were some values taken during that period that were outside, and it was seen as significant that it was more than 10% of the measured points taken. Because 1 or 2, you would say it's either someone turning a fan coil on or someone walking past. In this case, it was a generalized peak due to the fan coils actually not being able to control the temperature hugely well. The client also had other desks monitored, and a significant number of them still failed on either 1 or 2 or all 3 of these criteria as well. Sometimes too cold and sometimes too hot, and they actually had to redesign all of their fan coil units throughout their entire building over 6 floors. Next, this is a supermarket we tested. This is actually a mock-up within our offices in one of our laboratory spaces, and these are 2 separate tests. One is on the left is without food actually on the shelves, and the right-hand image is with food on the shelves. And this one is just showing that there is a significant difference from small changes within the space, and in this case, whether they were fully empty or fully populated shelves. Obviously, normally a supermarket doesn't have empty shelves when you go there, but it was an indication to the client that they could improve their energy usage. That's what this was actually based on, but it was also thermal comfort slightly, by just changing the way that they put their shelves in and how much food they actually kept on the shelves and the distribution of that food and how much, therefore, cold air dropped out of the front into that internal space. The actual air temperatures you can see in the bottom 2 images only ranges from 0 to plus 8 degrees, but there is still a large stratification within the space on the left-hand image, less so on the right-hand image, which meant that actually it was a better thermal environment with the food in because there was less temperature difference between your head and your foot height, which was a bonus for the client, and they actually felt they could then improve their energy efficiency by doing certain items within their cabinets. This is actually taken from an on-site measurement. This one has a slightly different range of PMV. This is a PMV image, and then a photo, obviously, of during the measurement. The PMV range is from white at -3 to only -1 for the orange. So you can see that it has a very depressed set of thermal indices. You know, the PMV is very low, as you would expect, it's a cold aisle within a supermarket. But this is showing that the stratification throughout the space was seen to be the same during our mock-up and on-site measurements. So we could actually prove that any improvement that we could make in the work that we did in-house should be able to be worked in the actual environment that it was going to be installed in, because we got good correlation between laboratory and actual site measurements. Okay, one of the second to last set of images. This is another office, another set of chilled beams. This one was actually looking at a significantly higher heat load than either of the other two offices. This is for full occupation, full heat load from the solar, the sun actually beating down on the windows. So it's high summer and actually the sun is out, and without any buildings around this building actually shading it from the sun actually coming in. And as you can see, the chilled beams are not able to actually hold the temperature even below 25 degrees throughout most of the room, which is seen as quite outside of their thermal comfort. However, this was the absolute worst case if they did nothing to redesign their solar shading and reflective coatings on their windows, and they had full occupancy in the room. The next image shows a slightly better example of the occupancy levels within the space. So this would be if people were either on holiday, especially during the summer. This is when people are more likely to be on holiday. And this particular office, they estimated that I think it was about 20% of the people would be out. And that actually significantly improved the air temperature because there was no equipment that the people were using actually on. So all of their computers could be turned off while they weren't in the office. And as it was a high density set of computers, this significantly dropped the air temperature within the space and gave them better PMV and PPD values. However, they still hadn't done any simulation of the solar shading or reflective coatings on the windows. That's what the next image was for. Then they added the simulation of the buildings around them as if they were actually still there, and solar shading and reflective coatings. And they actually got such good PMV and PPD values that they're able to say that it was a genuine pass. And it was only during the few days that the certain office would be fully populated that we'd need to do something about having localized cooling added to improve their thermal indices and bring the temperature down within the space. This is still using the lower occupancy levels, so that 80% occupancy, but it does give them a very good indication of their normal case of summer for their build. Last mock-up, this is of swell grills. So this is trying to cool the space down from grills in the floor. It gives they're trying to use swell grills to distribute the air nicely within the space. In this case, it uses essentially it uses the floor void as the ductwork to supply the air to these grills. Because of the high amount of air moving within the space, and they had swell grills under the desks, which are the black grey boxes in there, as well as in the aisle down the middle, they had a skewed air pattern from the swell grill. It was all going off to the left, as in this case in this image. And all of the swell grills were having exactly the same issue, and they were all peeling off to the left because they're all affecting each other. And especially the amount of air they tried to push through these swell grills was having this effect. The actual air temperature is reasonable. The PMV looks reasonable. The issue is the client had estimated the clothing level to be higher than they actually were going to have in the final build. They had a value that they wanted to do as a worst case, so it did give a reasonable PMV, but the stratification from the temperature was causing PPD values that were above 15% in certain areas within the space, especially under people's desks around their ankles. Although that's not shown in this image, we did a smoke test to show the air pattern within the space, and it was all hugging the floor under the desk. So the client decided to try and move all the swell grills into the central aisle to try and stop it affecting the people under the desks. And as you can see, it actually made the situation worse because they had then stratification within the room, and they had issues with still the pattern moving off towards the left as you're looking at it in our image, and causing PPD values that were still relatively high. Finally, a successful test was to put square grills underneath the desks to cool the computers locally, so they could put less air at a warmer temperature slightly through the aisle, and then they got this perfect swirl pattern. As you can see, it's got two lobes, it's coming down as a cone, and it's coming out as a perfectly uniform mix. And their PPD values started to drop towards 10%, and they actually were able to say that that was a pass, especially underneath the desks, where then people's ankles weren't getting drafty and cold. So it was a very good show that the adding extra grill did not make it actually better underneath the desks. It was actually, they had to think about their design and actually implement it correctly. Okay, so finally, I'd just like to do a quick roundup of the presentation. There are two main standards, BSRIA ISO 7726 and 7730, which is the instrumentation used and the calculations done on these numbers respectively. Thermal comfort, as an aside, is the thermal condition of a person within the space and how they feel about that space. It's mainly using the actual calculations done and therefore empirical numbers to actually work out how someone would vote if they were given a survey. You should always plan for comfort criteria from the get-go. So if you can, consider where people are going to be placed, where they're going to be sat, where the equipment is going to be, and what sort of temperatures you expect off of these pieces of equipment, especially from the manufacturer's point of view. And if you're a manufacturer, think about how this data would be used by a client trying to design their own office, and how they would actually use it to plan for the distribution of people within their space. Temperature isn't always the most important number. It's definitely a significant number, but as you can see, actually moving the airflow around, even though the air temperature was the same, actually had a much better effect on certain tests that we have done just to distribute the air differently. And finally, people can adapt to their clothing to actually fit within their space and feel better about the comfort, their thermal comfort within the space. So even though it says 5% for PPD is the lowest value you will be able to measure with our equipment, generally you will get better than that because people are able to either sit up or slouch or take a jacket off or put a jumper on to actually improve their condition within the space and actually give better indices and therefore hopefully less complaints for the actual operators of the building. Thank you very much. If you have any questions, as we said at the beginning, please put them in the question box and I'll answer them as soon as possible. Thank you very much.